Alright, so welcome back again in another repair video. Alright, this is Chipmaster here again. Alright, so today I'll be repairing a MacBook that I got yesterday. Right, so they want it back for today. That's why I'm doing this video. So I say let I just do this repair as a repair video case, right? It's a MacBook. I don't know what model it is. I got it as is in this bag. Right, it also has a cover back and front on the top and the back. Alright, or top and bottom I should say rather. Alright, so it's a tape here, so I'm removing the tape. And they say that it's not turning on. It's very urgent. Alright, so I need to keep this bag safe. Alright, so I'm going to take off the back. It seems like it's an Air. It's an Air. It's a MacBook Air, yes. So I'm removing the back cover. I want to see if it's a A1932 or A2337 or A2179. A2179, as you can see. Let's see if I can zoom and grab it. So it's a A2179 and that's a T2 model. It's a T2 Intel based model. Alright, so I'm going to plug in the power. Over to this camera. Alright, so this is USB-C power supply. Alright, so I plug in the charger. I get 5 volts and it's not boosting, as you can see, and I have 80 milliamp there on the screen on the DC power supply. It goes to 20, it goes back to it. So take a look at the pattern of the DC power supply. I got 80 milliamp there. Right, I have 5 volts here. Alright, see, it goes back to 1 and then it goes again up to 80 milliamp. So this is the pattern. It's going in it's doing it in a loop. Alright, see, as you can see the sequence of the DC power supply. Let's try, I'm trying the other port. 5 volts. It goes to 80 milliamp and then it goes back to 0. It tries again. See, it even turns off the entire USB-C supply power meter. Wow, it's doing something different on this one. Let's go back to the next one. Let me go back to the next one and see what it is, the output. So I can observe the fault. Alright, 5 volts, 1 point, it goes to 80 milliamp. And then it goes to 5, 2, 1. But on this side, so as you see, it even shuts down the entire USB-C meter here. So that indicates, so that is basically telling me that I have a short somewhere. Alright, so by judging, right, so by judging it there, it is telling me that there's a short somewhere on the power delivery section. Right, I don't think there's a short on PP bus. I think there's a short on one of my power delivery chips. So to confirm that, I'm going to use the USB-C testing tool here that I have here. So I'm going to check this one. Oh, that's the mail, sorry. All right. Alright, so I'm going to go to the diode mode on my meter here. Alright. Okay, so I had to restart my multimeter software. Alright, so I'm checking on VBus. I have 132. Okay, and this is on the B side. So this is A12345, which is B5, which is the configuration channel, and I have 573, and I have ground. Yes, I have ground. Ground is good. I'm going to flip over to the A side now. Alright, so VBus 132, right, A5 573, all is well. Alright, so I'm going to the A side of the other port. So I'm not sensing a short so far. VBus 132, okay, and B5 576. Alright, so I'm flipping over to the A side. A side, A5 576, power VBus 133. Interesting. So I'm not finding a short there. So could it be that PP bus is shorted? I'm thinking we'll have to take it apart to see what's going on inside. So I'm going to disassemble the unit. Alright, so the infamous A2179. Alright, so first of all, if I remove this in the other video, it was the A2337 where I removed this IO cable from the audio board. The laptop actually boosted, but it still didn't turn on effectively. So I found out that the audio amplifier was bad, so I'm going to do the same again. Oopsie. Right, audio amplifier, sorry, the audio board is now disconnected. Alright, so I'm going to give power again. Let me see. And it's same thing. As you see, the current is now here 8. It's the same thing, so it has nothing to do with PP bus. Alright, going on to the next port. Same thing. As you can see, nothing changed. Alright, so I will continue. First of all, let me just inspect the board here for any liquid spill or any corrosion or explosion. Alright, so this is the T2 and this is the T2 PMU IC. Alright, so as you can see here, all here, this section here, the T2 and the Thunderbolt section here is okay. And as you can see, it's a very small board, so there's not much. This is the CPU and this is the backlight section. And that's it. All is well. It's clean. Alright, so the board is out. So now I'm going to flip over the board and see if there's any corrosion or explosion. Ready? After 2, 1, 2. All is well so far. These are the power delivery chips, right? CD3217B12. Alright, so this is the charging IC. All is well. Alright, we have these are the NANDs. And this is the backlight section. This one seems to have more components than the A1932. This one has a lot of components. We have Wi-Fi and we have RAM here. So this model has a lot of components, a lot of resistors and capacitors, more other than the A1932. Alright, so all is well so far on the board. Alright, so I'm gonna check PP bus. PP bus. Alright, so PP bus is any of these tantalum capacitors here at 544. All is well. Alright, so I'm just gonna check on PPDC in 18 volts. All is well. PP3V3, PP3.3 LDO. All is well. All is well. No short there. No short there. Right, so I already checked with this tool here, and it also gave me good reading, so I know that there was nothing wrong in terms of short. Alright, the A932. Sorry, the A2179. Alright, so I'm going to check all coils, 3 volts and 5 volts. Alright, 3 volts and 5 volts section is good. Right, CPU, this is the CPU core. That's a bit high. Is that BCCSA? Let's see the next one. Alright, this is CPU core. CPU core, this is the graphics. Yes. This one. Is it PP bus? This should be PP bus. Yes. So there's no obvious short on any of the coils. Oh, this is the PP 2.5 volts for the NAND. 359. Alright, around the T2, this is PP 1.8 volts awake. 354, excellent. PP 0.8 sleep, excellent. The other, excellent. The core supply now for the T2, 13, excellent. Right, and this is the SRAM, excellent. So there's no short on T2 main power rails. Alright, VCC PRIM 3.3 488, that's excellent. So there's no short. So I'm going to connect the Type C port. Okay, so the Type C port is now connected. Alright, so I'm going to plug in the power. Alright, so this is the one that is giving the trouble. It seems to me that this is a BIOS problem, because this side is giving us 35. The USB-C meter is not shutting off, and then I plug it on this one, it shuts off the USB meter and does that in a loop. So first I'm going to check the working conditions of the power delivery chip. So I'll head under the microscope. Alright, so as you can see there, CD3217 B12. Alright, so the EPROM chip for this one, I believe it's beside the under here for the T2. I'm going to confirm it's schematic. Okay, so I'm here on the Shenjajao. Alright, so the board number is, as you can know it, so it's 820, right, hyphen, right, and the 01958. 01958. Alright, so the board view is here, and I'll open the schematic as well. Alright, so the power delivery chip is here. Oh, here is the chip. This is the RAM chip. I see it right as I open the board view here. Alright, so it's U3060. As you can see, this is the EPROM chip. Right, so U3060. Here is it. It's a RAM chip or EPROM chip, and it's 8-bit, which is a 1 megabyte in capacity. Right, so we have chip select, we have clock, and we have data input and data output. Right, this is a form of the pin number 2 and 5 is going to be used as the input and output. Right, so normally on older BIOS, right, so on the older BIOS, it uses the 4-pin, right, chip select, data input on pin number 5. Sorry, pin number 1 chip select, pin number 5 is data input, pin number 6 is the clock, and pin number 2 is the output. That's the order in which normally we check a BIOS RAM or an EPROM chip, right, on a computer system for laptops or even desktops, right? So now, because of the newer models developed, they've had to figure a way out to read the EPROM chips a faster way. So they developed something called the quadruple SPI bus. So where a pin can act as an input and an output. So on older BIOS, pin number 2 is specifically an output pin, which is going to send the data to the device that is reading the RAM, right? So on newer models of computers and other electronic devices, right, pin number 5 is acting as an input and output, while on the older devices, pin number 5 is strictly for input, which is data input. So this is a flexible way, which is used for the flexible I/O on the which is a flexible I/O bus, which is starting from Intel Series 8 upwards, right? The flexible I/O bus is a bus that is an expansion bus that is responsible for expanding your capabilities or the performance of the computer system, such as your Wi-Fi, your hard disk, which use PCI Express 4, and we have PCI Express 3, PCI X 3.1 specification, and so forth, which is configured under the flexible I/O. So this is why they developed the quadruple SPI, where the BIOS EPROM chip can act as a specific pin can act as an input and an output at the same time, right? While older boards, it only can act as input, one way in and one way out. So newer boards have a two-way communication. So a pin number 2 can act as input and output, so that the devices can read and write faster to the RAM chip, right? So this is called the quadruple SPI. All right, so the quadruple SPI, which is this, as you can see, pin number 5 is acting as a data out, and we have data in, right? We have data in and data out. So as you can see, I/O means it can act as an input and output, right? As you can see, number 3, pin number 3, write protect, it also acts as an input and output, right? So we have 0, 1, 2, 3. So that's 4 bits, right? So this is a new quadruple SPI bus, right, which is replaced by the older SPI, right? So as you can see, the reason is for the Thunderbolt chip. So the Thunderbolt needs to read and write to this RAM. So as you can see, and it is a shared RAM. It is shared between the embedded controller, which is shared between the power delivery chip, right, and the Thunderbolt. So the Thunderbolt needs to read it, right? So the Thunderbolt needs a fast way to access the data at all times from this RAM. So that is why they developed this way to allow a pin to read and write, which is allowing an input and an output pin, right? As you can see, so we have data input, data output, right? We have input and output, right? So the Thunderbolt can read and write quickly to this RAM chip. So this is the procedure of the quadruple SPI bus, right? So at this moment I'm interested in pin number 1, which is the chip select, right? So this is a Thunderbolt chip select, right? And I need to go back to the this chip, which is the power delivery chip. One is the master and one is the slave. I'm not sure which one, so this will tell me. So I'm going to search for the page here. So U3200, which is this one, right? This is U3200 and this is U3100. All right, so U3100, I don't know if it's the master or the slave. So let's go to the SPI. As you can see, U3200 is the master, right? So it's master out, slave in, as you can see, right? Master out, slave in. So this is the master, and this is going to, sorry, as you can see, it's all grounded. My mistake, please. That is my error. Sorry about that. As you can see, it's all grounded. So U3200 is not the master chip, which is going to read the EPROM chip, right? So as you can see, we have this one. So let me double click, search again. U3100 is the master, as you can see, chip select, right? SPI SS. Now we have signals, right? So we have UPC underscore SPI clock, we have UPC underscore X underscore SPI underscore chip select underscore L, and this is the one that's going to read the BIOS, the RAM chip, sorry. So the RAM chip is going to be read by U3100, right? So in order for U3200 to read it, has to go through this chip in order to read it, and this is done through something called a UART, right? This UPC UART underscore RX, and we have TX, right? So UART stands for Universal Asynchronous Receiving and Transmitting, which is a small data transfer speed of data between two devices, right? UART, Universal Asynchronous Receiving and Transmitting. So RX is transmitting and RX is receiving. So this is the way how they communicate. This is a very important and crucial signal. If this signal has a blockage or there's a fault on this line, then you can't get 5 volts boost to 19 volts and your laptop will not turn on, right? So this is a very key signal, as you can see, UART, right? So I'm interested in this one, which is the UPC underscore X underscore SPI underscore chip select underscore L, and I'm going to search. All right, so as you can see, it's coming to a 15 ohm resistor here, right? This is R3096, and it's been renamed to TBT underscore XT underscore SPI underscore chip select or CS underscore L. All right, so I'm going to search for that one, and as you can see, it's coming back to this same chip, right? Because it is shared with the Thunderbolt chip, and the Thunderbolt chip is an Intel based chip, so the Intel chip needs to read this EPROM chip, right? And I already explained the pinouts for this quadruple SPI RAM chip, right? So chip select is going to be pulled up by R6036, and it is connected to PP3V3 underscore UPC underscore X underscore LDO, and this signal is generated by any one of the power delivery chips that is plugged in, that will automatically generate this LDO, right? So LDO stands for low dropout, which is a very small current of about 100 to about 300 milliamp maximum pin current. All right, so I'm going to check on this resistor here, which is R3060, and it is connected right beside the EPROM chip here. So I'm going to get the oscilloscope as well to see. Let's go under the microscope rather. All right, so this is the RAM chip. So I want to check here if I'm getting a reading. Right, this is the resistor here. All right, this is the RAM chip, and this is the resistor here. That's the resistor, and that resistor, which is R3063. So I will get the oscilloscope. Okay, so I'm now under the microscope with the oscilloscope. All right, so I'm going to plug in my power, but I need to capture this because it only at a single trigger because the signal only come once. Alright, so I'm now under the microscope with the oscilloscope. Alright, so I'm going to give power. As you can see, I have a reading right there. So the power delivery chip actually reads, right, and that's a beautiful wave there. So the master chip, as I said before, is this one, right? Oh, all right, sorry about that. All right, so I'm under the microscope now. All right, so this is the EPROM chip. All right, so the EPROM chip is right here, and this is the resistor. This is a pull-up resistor, so I'm checking on this side of the resistor. All right, so I give power. The power is there. Let me see. All right. Alright, so I'm waiting for the loop. Alright, there we go. So we have a reading. We have a reading right there. So the EPROM chip is actually reading, as you can see. Right, so that's a nice, clean, stable waveform there. And that indicates that this is the master power delivery chip. Right, and it's reading its EPROM. Right, so next I'm going to plug in the power inside of the other port that is giving the power on off sequence, right? So I'm going to look for so this is the master and this is the slave. All right, so I'm going to look for the UART bus to see if this chip is communicating with the master chip. All right, UART, I'll just choose this one, RX. Alright, search. That's not it. Oh, I can check here. Yeah, I can check here. Alright, we have a 1 mega ohm resistance there to ground. If I remove this resistor, definitely no boost. Very important resistor there. Alright, so I can look for this resistor. It's R3105. And that's right beside it, right there. Alright, so this is the resistor. One side is grounded. Alright, one side is grounded. And this is the grounded side. This side is grounded, so I need to check here to see the communication is done between these two power delivery chips. Alright, so I'm going to give power. Alright. Alright, so I'm checking here. As you can see, there's a wave. Let me go again. Alright, so I'm waiting for the power to suspend. Alright, I got a wave. Yes, I did. Let me go again. I'll move the power. Plugging in the power now. There we go. So the chip there is communicating. As you can see, we have a nice communication there, and that indicates that the chip is communication is good. But you can see there's a loop. See, loop. Right, does it again. Stops. Does it again. All right. So the loop. Let me see this one. This is the pin that the port that is giving me the on-off problem. Yes. Alright, so I'm going to program this EPROM. I will remove. Okay, so I have here the programmer. It is the USB-C RAM Assistant U301. Just cleaning the contacts so that I can get a proper contact. Alright, so can see pin number 1. Okay, it says already aligned for pin 1. Alright, so the RAM chip is inside the, as you can see, the RAM chip is in the socket there, so I'm going to close it. Okay, so I'm now in the software on the drive. Alright, so this is the AS programmer, as you can see. Alright, so I'm going to select read ID. What? It says that the chip is not found. I should please make sure that the chip is not blocked by the socket or what the. Alright, so this is the translation. Let me translate it for you. Okay, so this is a donor board I have here. Alright, so this is the RAM chip. Alright, any T2 base or T1 base board can work. They're all the same size, 1 megabyte. Alright, so I will just tin here with some fresh flux and just clean the chip, and I will re-tin with some flux and with some low melt solder here, so that I can have a proper contact in the programmer. Alright, I want to make sure that my connection is spot on, no mistakes, no extra work. Alright, so there we have it. So it's clean and shiny. So I'm going to remove the programmer. And I'm going to put the programmer inside the RAM chip in the programmer. Alright, that's the red mark there for pin 1. Alright, that red mark indicates pin 1. And pin 1 is right here. Let me clean here. Clean the surface of the chip here. Oh. Alright, so that's pin 1. Not sure if you can see. Alright, chip is dead spot there in the middle. Alright, so I'm going to head over to the software and read. Okay, I will close and I will reopen. There we go. There we go. So as you can see, this chip is now red, right? This chip is now red. Let me read again. All right, so this is the one I need. This is the 8 megabyte. It's a W25Q80DV, right? 3.3. Right here it is. So it's a W25Q80D, right? V, and that's the chip I need. All right, so I'm going to select that one, and I'm going to open a file. So the file that I need is we are working on a A2179, and the chip is U3060. As you can see, this is the file. I'm going to click open, and then I'm going to click auto, and this IC will be erased and programmed. Continue. I said yes. So now the chip is being programmed, and now I will wait. All right, it's now right in the memory, right? Programming memory. Verify. All right, excellent. So it's finished. So I will close the programmer. All right, so I will solder this now back to the board. Just tinning these pads. All right, it's now ready. Right, so pin 1 is here. And I will solder. Moving the excess solder. Now cleaning. All right, so now I will now measure the resistance. On pin number 1 and pin number 8. All right, pin number 1. Oh. All right, checking again. Pin number 1. I get 552, which is good. Pin number 8. 458. Excellent. So I'm going to plug in the power. Give power. Okay. Now I'm going to check chip select again with the oscilloscope. Okay, so the oscilloscope is now up. Alright, so I'm checking back on this resistor here. Alright, for pin number 1, chip select. There we go. We have a better reading now. As you can see, I have a better reading. As you can see, the current is now increasing. The current is now increasing. 400, 500. Excellent. Ha ha ha. And I have a boost. Alright, so let me check on the other signal for the slave. UPC underscore UART underscore RX. So I'm going to check that signal now for the communication. And that's the resistor here. Alright, right here. I'm going to give power. Take a look at the oscilloscope. Okay. So what I observed is that when there's a fault, there is a reading. There we go. As you can see, the reading is now established clearly, and that indicates now everything is perfectly fine. As you can see, the reading is only once. So let me go again. So we get about 2 to 3 jumps and it stops. So the communication is complete, right? So let's go again. There we go. 2. So we get 3 jumps, 3 communication jumps, and that's it. And the communication is complete. All right. So now I will plug in the power. This is the bad. This was the port that was giving the issue where it keep jumping. It turns on, off, turns on and off. Now I have this 19 volts there, and as you can see, the unit is now, the current is now pouring, and it is taking current, and the system is on. As you can see, 212 milliamp there. Okay, and that's a done job there. So I hope you. So sorry, I'm going to assemble the unit now, and then get back to you immediately after I'm finished with this part of the assembly. Okay, so the unit is now assembled. Let's see if it's on. No, battery is dead. All right, so I plug in the power. There we go, Apple. All right. So it was definitely the RAM chip was bad. I don't know if you can see. Okay, something is fishy here. It's not loading. The fan is not spinning fast. fan is not spinning fast. So what happened there was that it didn't shut down properly, so it had to do a kernel panic. So now as you can see, I'm on the login. So that was happening, so it had to do a restart because of the kernel panic. It didn't shut down properly. As you can see, the battery is charging. I'm getting 1.8 ampere of current there. Alright, so there we go, there we have it. Alright, so all is well there, and the unit is powered safely and secured, and it's ready for the customer to pick it up for this emergency repair. Let me fix this properly. Alright, so there you have it. I hope you enjoyed the video, and I hope to like and subscribe. As usual, let me know in the comments about this video. Thanks to this tool, right? This tool did the job, right? And it's called the U301. Alright, so bye again, and happy Easter everyone. Bye.